Now let's look at application of what I call multi-function case, the operational rule of derivative for multi-function case. Okay, so that means there are multiple functions in this case. So here, fx equals to, this is the first case, which is these two functions are summed up or deducted. Okay, so fx equals to gx plus or minus hx. So basically, plus and minus, they are actually the same thing, because minus can be viewed as plus a negative version, right? For instance, y minus 2 can be viewed as 1 plus negative 2, right? So plus and minus, they are basically the same thing. So as you are understanding this, you can put them in the same sort, and the derivative actually follows the same rule, which is just to derive them, derive each component, and then if they were originally added up, then add them up. If they were originally deducted, then apply the deduction. Okay, so here also I'd like to further explain why for this linear function rule, the result is this. Okay, so actually in my illustration, I was previously focused on fx equals to m times of x. And I've shown pretty clear in the previous slide that the derivative of the, of the first part of this addition should be m, right? But you can also consider plus b, and here b is another function, which is a constant. And then the derivative of this constant equals to 0, so the result, which is the derivative of the entire thing, mx plus b, equals to the derivative of mx, which is m, plus the derivative of b, which is 0, because that's a constant. So the result is m plus 0, which is m. That's the derivative. So this is how you can view this entire thing also as an application of this sum and differences rule. Okay, so now let's look at one application of it by looking at my document camera. So the first, which is plus or minus rule. That's what I call it. Okay, plus minus rule. Easy to remember. Okay, so here what you do is, so if fx equals to a plus or minus result of two functions, then its derivative is just the derivative of these two components, and we keep the plus or minus operation. So now the one that I'm looking at is fx equals to 10 times of x minus 2 times of x cubed. Okay, so for this one, its derivative is the derivative of the first one minus the derivative of the second one. Here, prime is used to note the derivative operation. Okay, so 10 times of x, the derivative of this is just 10, right? Minus, we keep it here. And here, 2 times of x cubed. If you don't remember, you can refer to the previous one. It is actually the power rule, right? And here f prime x is k by n x to the power of n minus 1. And here k equals to 2, n is 3, and x to the power of n minus 1, which is 3 minus 1. So the result is 10 minus 2 by 3 is 6 to the power by x to the power of 2. Or you can further simply write this as 10 minus 6 times of x cubed, x squared. So this is one application, okay? And now let's look at the second one, which is the product rule or the multiplication rule. I'll use this star to note as multiplication. Okay, so the product rule is a little bit more complicated, but if you're able to recognize those components, then what you're doing is basically plug everything in. So what you are doing here is you apply the derivative to one of the two multiplier, right? So apply the derivative to the first multiplier, keep the original form of the second, keep the multiplication, okay? And then keep the first one as the original, apply derivative to the second multiplier, keep the multiplication. And these two parts should be added together. So now let's look at one example. Fx equal to 2 times of x cubed by 4x minus 1. Okay, so if you ever get confused, or if you're afraid that you may get confused, what you can do is, here I can write on the side, what is gx? Okay, that's 2 times of x cubed. What is hx? That is 4x minus 1. Okay, then you can further do the derivative here. Just do things step by step. Or if you do this in an exam, you can at least get some partial credit for steps, right? So here, g prime x and h prime x. G prime x, again, we're applying this power rule, right? So g prime x, in this case, the k equal to 2, we keep it here. The n equal to 3. So here for its derivative, we first write it down. And then for the x term, we keep the x, and for its power, 3 minus 1. So that is 6 times of x cubed, x squared. And for the second one, it is a linear form, right? We can disregard this term as we're taking the derivative, this constant. So then the derivative of this is just the slope, which is 4. Then for the derivative of the entire multiplication, what you do is just to plug things in, right? Into this formula. So what you have is, okay, g prime x, that is 6 times of x squared, right? By hx, 4x minus 1, plus, now we use dot to note for multiplication because we have x, right? So plus gx, which is 2 times of x cubed, multiplied by h prime x, which is 4, right? Then you can rearrange it. So here it is 24x cubed minus 6x squared plus 8 times of x cubed, which is 32x cubed minus 6x squared. I would consider this as a neat presentation of the result. If you want, you can, but it's not necessary. Drag x squared out. So here we have 32x minus 6. Both answers are acceptable. Okay, so that is the second one, the multiplication rule or the product rule. The third one is the division rule or the quotient rule. So here, fx equals to gx over hx. Okay, then f prime x equal to, now it's similar to the previous one, okay, because division is the inverse of multiplication, so they do have some relationship with them. Okay, so the numerator is g prime x hx minus gx h prime x, and the denominator is just the original denominator squared. Okay, so here, because in the previous one, in the multiplication, whichever you apply the derivative on first, doesn't matter. The sequence between these two doesn't matter because this is just a simple addition, right? A plus B equals to B plus A. You flip the sequence, it doesn't matter. But here, for the minus, for the subtraction, the sequence matters. 1 minus 2 is minus 1. 2 minus 1 is positive 1. These two are not the same, right? So here, what you should know is, for the same position, gx, now it stays on the numerator, then we apply the derivative to this term first. We apply the derivative to the term that is original in there first. And then we start from there. So if you apply the derivative term to the numerator, right, because it was original there, and then you multiply it to the other term, and for the other term, you keep the original form. Add a minus, then keep the original form, and apply the derivative to the other one, which is the denominator. Okay, so now let's look at one example, which is x squared minus 1 over 3 times of x. Again, what I strongly recommend that you do, especially if you are not very confident with your math, is to write things in steps. Gx here is the numerator and hx is the denominator, right? And then g prime x is, first apply the power rule to this. We have 2 times of x to the 2 minus 1, which is itself, right? Minus 1, its derivative is 0, so we can omit. And then h prime x, here it's just a linear case. The derivative is just its slope term, which is 3. Then we just plug everything in. So here we have g prime x, which is 2x, multiplied by hx, which is 3x, right? Minus gx, which is x squared minus 1, by h prime x, which is 3, over hx, which is 3x, it's squared. So we have 6x squared minus 3x squared, and here there is a double minus, which is plus 3. Okay, so it's minus 1 by 3, which is plus 3, over 9 times of x squared. So the result is 3x squared plus 3 over 9x squared, and we have a same 3 to cancel. That is x squared plus 1 over 3x squared. Okay, so here is the demonstration of multiple functional case by adding up, by subtraction, multiplication, and division. Thank you.